in example 20, we're going to apply some of those properties of the scalar product to simplify these expressions. All right, so let's have a look at question A. Question A is asking us to simplify this, so I'm just going to use what is like the distributive property of it. And actually in this question, I'm not going to do the underlines because there's too much algebra to do, okay? So B dot A minus C. So A dot B, okay, so because as you know, it goes across the brackets like pretty much like the distributive law. And that's A dot C, and then we've got minus B dot A, and minus B dot minus C is plus B dot C. And remembering that A dot B is the same as B dot A, so these two cancel out, so we're left with A dot C plus B dot C. And they're wanting us to leave it simplified or expanded like that. You could go another step and say that that is actually equal to A plus B dot C or vice versa, but you don't need to for this question. All right, so part B, we're going to look at, well, it's got two parts. So let's expand the following here. So we've got A dot B, A plus B. There would be these things here normally, but as you know, I'm not really doing it for this question because it gets a bit messy with all these things. Okay, so A dot B, in the same way you could break it up in that you could say A dot everything in this bracket plus B dot everything in this bracket, but we'll just do that step straight away. So we've got A dot A and A dot B. Oh, okay, I'm not going to do these, but I'm going to get rid of them. And now we've got the B plus B dot A. There's only pluses here, so don't need to worry too much. And plus B dot B. Stop it. All right, so A dot B is the same as B dot A, so that equals A dot A plus 2 times A dot B plus B dot B. Does this look like anything to anyone? If we look at the brackets and we look at what we've got here in the end. So anyhow, let's move on to the next one and see what happens here. So we've got A plus B dot A minus B. Where's that come from? Okay, so A plus B dot A minus B. And once again, we could expand in one extra step, but let's just go, let's use this property. So we know that A dot A exists and A dot minus B, so that's minus A dot B. And then we've got plus A dot B or B dot A, and plus times minus is minus B dot B. These two cancel out. Plus AB is AB is equal to BA, so on and so forth, so they cancel out. So this equals A dot A minus B dot B. So if you were to go ahead and if you had have put all those things together to begin with, so A plus B, if you expand them out component by component, so you'd have A1 plus B1 times I, and A2 plus B2 times J, so on and so forth. We've pretty much ended up with something that looks just like a quadratic formula, so to speak. So this is the sum of perfect squares. Sorry, well, not sum of perfect squares, but squaring a sum. And this is the difference of perfect squares here. Okay, part 2. You can see, and as we saw in our properties, A dot A is actually equal to the magnitude of A squared. And the same goes for B dot B. So that's what that is. And that would be, so it's the magnitude of a squared and the magnitude of b squared. And of course you could use the cosine rules, etc., and find out what that is. But that's quite interesting, don't you think? All right, let's move on to example 21. So this is just using these properties to find a solution. We have, let's pretend we have this vector here and we dot. We're not exactly sure what vector, but we've got these restrictions on I and k. So 3i and 2k on our second vector, and we need our dot product to equal 4. So that means that this 1 times 3 plus 1 times minus k, x, sorry, minus x, plus minus k, so minus k is 1, minus 1, times 2 is minus 2. We need all of this to equal 4. If we add 2 makes 6, take away 3, so minus x is equal to 3. Therefore, we need x equal to minus 3. So for our second vector here, if we had 3i minus 3j plus 2k, the dot product with ij minus k is equal to 4. All right, and that's just applying those properties we've already learnt. Okay, on with the exercise.